For over a century, terrestrial transportation has been dominated by a single engineering concept, the continuous pneumatic tire. But that dominance relies entirely on our built environment acting as a flat, two-dimensional plane. The moment that smooth asphalt disappears, the physics of a rolling wheel grind to a complete dead stop. This is the fatal flaw of conventional transport. In unstructured environments, wheels fail completely. During a major earthquake or flood, the resulting debris field instantly immobilizes standard four-wheel drive emergency vehicles right at the perimeter of the disaster zone. To solve this, aerospace and automotive engineers are building the ultimate mobility vehicle, or UMV. Look at the Hyundai Elevate concept. It abandons the rigid continuous axle. Instead, the cabin is suspended upon four massive, highly articulated robotic limbs. By replacing static suspension with mechanical hips, knees, and ankles, the vehicle can alter its geometry on demand. It can scale a 5-foot vertical concrete wall, or splay its legs outward to achieve a massive 15-foot track width to step directly over a shattered roadway. This architecture physically decouples the passenger cabin from the immediate topography. Rather than being trapped at the perimeter of a disaster, first responders can drive to the edge, stand up, and step directly over the impassable debris to extract critically injured survivors during the strictly mathematically vital 72-hour survival window. But pulling this off introduces a severe engineering tension. The act of walking is an inherently inefficient method of propulsion. It is essentially a controlled forward fall, which burns vastly more energy than simply rolling a wheel across a flat plane. With a wheeled vehicle, you only expend energy to overcome rolling resistance and aerodynamic drag. A legged system must continuously expend massive amounts of electrical energy just to fight the gravitational pull of the Earth, repeatedly lifting, catching, and lowering a multi-ton chassis with every articulated stride. This chart visualizes the deep infrastructural burden of electrical propulsion using data from the French Atomy environmental calculator. It takes 2.58 tons of oil equivalent as primary energy just to produce 1 single ton of electricity as end energy. Relying on heavy electrical draw for continuous stepping is a mathematical dead end. To mitigate this severe caloric drain, designers looked to space exploration for a hybrid architecture. Take NASA's Athlete rover. It perfectly synthesizes the high-efficiency rolling dynamics of standard wheels by placing them at the termination points of its articulated, multi-jointed limbs. Modern UMVs iterate on this by integrating non-backdrivable motors into their joint architecture. These specialized motors allow the heavy robotic legs to mechanically lock into a specific geometric configuration. Once locked, the electrical current is entirely severed, letting the vehicle suspend its cabin over a void without depleting its battery reserves to maintain the pose. Because continuous walking is thermodynamically indefensible for long-distance travel, these hybrids are designed to operate predominantly as highly efficient wheeled cars on flat surfaces, activating their energetically expensive walking mode strictly when geographical boundaries demand it. Even with the physics balanced, the commercial viability of these machines hits a brutal financial wall. The synthetic musculature generating all this movement is the high-torque electric servo actuator. This exploded schematic shows a premium rotary actuator, which translates electrical current into rotational force. It relies on 3 critical subcomponents: the frameless torque motor, the torque sensor, and a highly specialized gear system called a harmonic drive. That harmonic drive requires microscopic machining tolerances to achieve absolute zero mechanical backlash, meaning there is no internal wiggle room between the gears. Looking at the cost breakdown, manufacturing that single flexible spline accounts for roughly 36% of the joint's total financial footprint, with the torque sensor eating up another 30%. Until automotive conglomerates secure absolute vertically integrated supply chain dominance to manufacture these complex motors and harmonic drives internally at a massive scale, heavy walking vehicles will remain priced out of widespread consumer availability. But let's assume the engineering and economic barriers fall. These machines immediately collide with an urban environment, painstakingly engineered around the predictable physics of rolling tires. Traffic calming initiatives use rigid two-dimensional barriers to segregate cars from people. A multi-ton machine capable of elevating its chassis 5 feet in the air physically bypasses these defenses. It can step effortlessly over active traffic bollards, curbs, and the tactile paving installed specifically to keep blind citizens safe in protected pedestrian zones. This creates an acute regulatory paradox. The Volpe report, which examines automated driving systems, notes the extreme difficulty of applying traditional motor vehicle safety standards to machines that defy strict categorization. The 100 and 200 series safety standards require engineers to crash vehicles into rigid concrete barriers to measure crumple zones. But standardizing a side impact test is physically impossible when a vehicle's cabin height, wheelbase track width, and center of gravity can dynamically and unpredictably alter their dimensions at impact. Regulators integrate crash telemetry into complex models to project future safety statistics across the country. They currently lack the deterministic data required to accurately model the safety impacts of a machine that continually alters its physical geometry. At the localized enforcement level, the legal structure is equally strained. Standard traffic enforcement explicitly relies on citing a licensed human operator who possesses visual capacity and physical accountability. Recognizing that UMVs will largely operate autonomously, jurisdictions are innovating rapidly. California enacted Vehicle Code Section 38752, authorizing peace officers to issue formal non-compliance notices directly against self-driving technology when there is no human occupant. This completely severs the historical link between the physical occupant and legal liability. A standard traffic ticket instantly forces corporate defense attorneys to litigate algorithmic intent, sensor fusion data reliability, and machine learning decision trees rather than standard human error. The physical manifestation of the walking vehicle is complete. The kinematic algorithms tested by NASA and the electric servo actuation required to lift these chassis already exist. The ultimate success of these machines depends not on robotics, but on the capacity of municipal governments and global safety administrations to completely tear down and rewrite a century of architectural and legal definitions of terrestrial mobility.